Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, for those of you that are frowning, I'm not Ellen Prager, just in case that wasn't clear. But I will be, in the short time that I'll be speaking here, introducing Ellen. Ellen drew the short straw of the person in the proceedings that had to wear a wetsuit. And she's wearing the wetsuit, really, I guess that's a giveaway as to the domain that she's most active in, that of oceanographic research. Her biography you will see from the proceedings. I'll just point out that we should have very little sympathy for her, given that her research expeditions have taken her to such terrible places as the Florida Reef, the Bahamas, the Caribbean, Galapagos Islands, and Papua New Guinea, which I'm assuming will be sort of woven in, the experience of those woven into some of the insights that she's going to be giving to us as she takes us through eOcean, the challenges ahead and below the waves. So, Ellen.
Okay. Let's see. Test. How's that? All right? Probably. Well, thank you, Darren, and thank you to Microsoft for inviting me. It's a pleasure to be here. This morning and this afternoon has been really informative for me. I can think of a lot of applications from what all of you are doing to ocean science, but I'm also sure that you could probably think of way more than I can. So I hope this evening that I'll be able to inspire you to think about how you might be able to apply your work to ocean science and technology and communications, hopefully in ways that I can't even think about. Because the truth is, we really need cross-disciplinary efforts to solve very important major problems we have in the Earth's oceans. From overfishing to pollution to habitat loss, the impacts of climate change, and invasive species. All of these problems are going to take science and technology, understanding the causes and effects. We need to be able to transfer that information to the people who can then make policy and manage the oceans. And it's truly managing human activities on the oceans, not necessarily the oceans themselves. And then we also need to be able to use the information we gain to educate and inspire the public. And that is where my passion lays. And at the end, I'm going to save some really fascinating, cool images of organisms in the sea and their applications to society that you may not know about. That, again, I hope will inspire you to help us solve some of the problems in the ocean. But I want to start by showing you a few examples of where technology has really provided revelations in the sea. You could say they're revolutions in technology, but they're revelations in the sea. And probably one of the biggest that I know many of you here are familiar with is satellite imagery. Satellite imagery, here's a couple. I apologize for the elliptical nature of the Earth. It's a little stretched. But satellite imagery, this is sea surface temperature, so the surface at the very skin of the ocean, has enabled us to get a global perspective at one time that we never were able to get before. Imagine, in one point of time, if you just had to deploy ships and buoys and floats, nearly impossible. But now we can get a global image of sea surface temperature at one point of time, and we can then look at how it changes over time. And that's critical to understanding the problems that we face in the ocean and the effects of climate change. But it's not just the global ocean that this sort of imagery helps us to understand. It's also smaller scale features. This is a classic image from satellite imagery in oceanography. And now, of course, my laser pointer, oh, there it is. A classic image of the Gulf Stream. Here you see Florida, again, at sea surface temperature, so the warmer colors are warmer water. Here's the Gulf Stream coming up along the East Coast, sort of meandering off of North Carolina. And what you see so clearly in this image that we couldn't see before are these warm core and cold core eddies. Here's a cold core eddy that, like an oxbow lake, has pinched off of the Gulf Stream. Now imagine if we didn't know this, how our understanding was changed, not only in circulation dynamics and the transfer of heat in the ocean, but even more, maybe just as importantly, is, see, this green dot here. This is a cold core eddy. The eddy has encapsulated water from the slope up here, and the slope water is highly productive. And so it's a little pool of productivity that goes into a low productivity zone. So not only are we understanding circulation, heat transfer, but we're starting to understand issues of productivity. And I will tell you, in Florida, one of the things that we're learning is that eddies from the Gulf Stream are very important in training larvae for things like the spiny lobster population. So one of the questions is, if you have a planktonic larvae, how do you know where they're going to end up? Well, in Florida, we know some of the spiny lobsters stay in Florida because they get entrained in eddies that we can now see with this sort of satellite imagery. Imagery of ocean color, which is a measure or an estimate of the chlorophyll amount at the sea surface, gives us an idea of not only global productivity, but smaller scale features as well. I think it's pretty obvious in this color, ocean color image, where you see the red and yellow, that's the highly productive areas. Pretty obvious to this that it's a very small percentage of the ocean, in fact, associated with continental shelves and coastlines. Most of the ocean out here is a desert due to a lack of nutrients. But with this sort of imagery, we can also look at smaller scale features. One of the biggest problems we face in the ocean, and particularly in the coastal zone now, is harmful algal blooms. In southwest Florida, there's a real problem with red tide. It gets aerosolized and causes respiratory distress on the beaches and causes fish kills, marine mammal kills. Well, here's a satellite image of a red tide bloom off of Sarasota, and this kind of imagery not only allows us to track these red tides, but hopefully better understand them. We don't know what triggers them. We don't know what feeds them once they trigger, and we don't know what causes them to stop. So this not only helps us to track them, but hopefully satellite imagery is going to help us better understand them. From the space, we can also look at sea surface height using satellite altimetry. Here's a great image of sea surface height during the peak of El Nino in 1997. This red and white is elevated sea surface height. And during a strong El Nino, you get the warm water pooled over in the eastern Pacific in the equatorial area, and this has immense effects not on the ocean, but as we all know, on the climate worldwide. So here's a big warm pool of water just sitting off the coast of Central and South America and the US. Dramatic impacts not only in the coastal zone, for instance, shutting down upwelling off of Peru, but on the climate and weather in these coastal areas. So this kind of imagery has been enormously helpful in understanding these phenomena, but also in visualizing them and explaining them not only to students, but to the public and policymakers. In the deep sea, technology has truly been a revolution in terms of we found things that we had no idea were there before. In 1977, Alvin went down and following remotely operated vehicles such as Jason shown here, to discover hydrothermal vents and the chemosynthetic organisms that are associated with them. People didn't even imagine that far from the life-giving nature of the sun, these communities existed. We now know they occur in all of the world's oceans, and we think there are at least 280 sites of hydrothermal vents, most of which remain unexplored. In addition, while people think, oh, we've charted the whole ocean floor, we know what the sea bottom looks like. In fact, we don't. Detailed charts of the seafloor do not exist. And here's an image where technology is now allowing us to get much better imagery, much more detail of what the seafloor looks like with remotely operated vehicles and AUVs. We're also, with technology, learning what lives in the midwater realm. The midwater realm is between the surface waters and the very deep waters in the ocean, a place we call the twilight zone. And here you see from Larry Maiden an incredible image of a jellyfish. You know, before the advent of this sort of technology, you would drag a net through the water, and you'd come up with what we used to call sea snot, and you'd be like, oh, I think this kind of looked like this when you put it back together. We had no idea what these creatures looked like. Here's a really great example from Edie Witter at Harbor Branch Oceanographic Institution. This is kind of a devious thing. It's a cool, really cool picture. This barrel-shaped thing is a salp, and inside the salp is a female amphipod which has eaten her way into the salp, eaten the insides of the salp out, and now will use it as a lair to build a nest. We could never see things like that before advent of ROVs and submersibles. And let me just say, if that creature looks a little bit familiar, people suggest that it was what the movie Aliens, that alien was depicted after, was this little amphipod here. We're certainly getting a look at a smaller world in the ocean than we ever have. We now better understand hereditary histories through genetics and through molecular biology. But just looking at some of these creatures in real time live is giving us insights we never had. Now, I will say, if most people looked under a microscope and a little drop of seawater and saw what was in it, like in this picture up here, they probably would never go in the ocean, particularly if these things were any bigger. But here is an amazing image. And I have to tell you, I just got this for a project I'm working on. I've never seen anything like it. This is a live planktonic foraminifera. And foraminifera are amoeba-like organisms that live in spherical calcium carbonate shells. And during the day, they extend sort of protoplasmic-like arms and spines outside of the shell to feed. But what we're just learning, because of images like this, is they also have a symbiotic relationship with the dinoflagellate. See how those little brown dots? Those are a dinoflagellate that during the day, the foraminifera sticks out of its shell to use the sun in photosynthesis, and then at night pulls them back in. So its own solar-powered system. And honestly, I've never seen any image like this before, and again, it's technology that's allowing us to do it. With the advent of suites of sensors and the ability to integrate the data into computer models and then come up with visualizations, we're truly improving storm warnings and forecasts. Not only of the path of hurricanes and their intensity, which we're getting better at, we're not perfect at, but also predicting things like storm surge, being able to visualize storm surge and know what areas need to be evacuated. So those are just some examples, some really, I think, stunning examples where technology has made a huge difference in ocean science. And while we've made great progress, there are still a lot of challenges ahead, and there's plenty of room for innovation. And I will tell you that much of what needs to be done and what is going to happen involves the things that you all do. Large data sets, integrating data into computer models, figure out how to get access to different information at different formats, and then communicating that knowledge and information to other groups. So I'm going to give you just a couple areas where we're sort of on the forefront of ocean science and where we're headed, and some of the challenges we face in those areas. In terms of exploration, the technology is advancing. Now we're moving away, well, not we're moving away, but we're complementing submersibles and remotely operated vehicles with autonomous underwater vehicles that can be pre-programmed, go out, survey the seafloor or the water column, and then come back to either a docking station or a ship to dump the data. Right now, Woods Hole is developing a new Alvin, which will go deeper, be more maneuverable, and will have better viewing for the observers on board. That, again, is going to provide a whole new data set, a larger data set, because it's going to be able to go to more places in the ocean. The other interesting thing that's happening is the industry, the sub-industry, is starting to build these very small, deployable, maneuverable submersibles. Okay, a cushy part of my job, I just went out with the maker of this little Triton sub who was showcasing it for potential buyers, millionaires who wanted new toys. But the idea is, so you get somebody who buys one of these and puts it on their yacht, they could invite a scientist to go out with them, and while they're enjoying the fruits of their labor, having a sub ride, they could bring a scientist to do it as well. And I got to go down in this sub, and it was incredible. There's very little infrastructure right in front of that acrylic shell. So we were in Bimini in the Bahamas, and we were about 2 feet from a wall at 300 feet. And just incredible view. These also, so you could use them for science, you could use them in the tourism industry, and you could use them coupled between people who want them as toys, but then as a great way to do science. And I actually think that's a new model. As funding gets less and less, we have to be entrepreneurial about how we do our science, and I think that's a great example.
I think Paul Allen has one, but Larry Ellison
Yes, too. We need to talk to him about some science. Well, one application for AUVs where the whole idea of integrating sensors into AUVs is like that red tide problem I was talking about earlier. This is Gary Kirkpatrick from Moat Marine Lab in Sarasota, and he's created what he calls the Brev Buster. And he's integrated an optical sensor into this AUV that goes out and looks for concentrations of Carinia brevis, which is the dinoflagellate off of Sarasota that causes red tide. And he recently launched it, and I will say, if any of you saw the headlines, "Where's Waldo?" I'm not sure they should have named their AUV Waldo, but one of the problems with AUVs is, and submersibles, we don't have a good communication and tracking system. They lost this AUV, and so their big headlines was, "Where's Waldo?" So they found it washed up somewhere else, or somebody else found it. But this is a big issue in science. AUVs have been lost because we have poor communication and tracking technology. Exactly. Water is just terrible. Well, here's a little red tide humor for you. This sign went up at Siesta Beach during a strong red tide. Red tide is still in our area. Sorry. The good news is you don't have to worry about the sharks. You got to have some sense of humor. Well, you heard a little bit about this from Tony's talk this morning. One of the priorities of research in the ocean community is to develop integrated ocean observing systems. And you can think of it as similar to what we have for the weather. You know, we get great weather forecast models because we have so many observations. We don't have that in the ocean. We don't have it on the seafloor. We don't have it in the mid-water column. We don't have it on the surface. So the idea is to be able to create an integrated system using all these different technologies. The Ocean Observing Initiative has been funded and is moving forward. There are already some regional operations in place. And I will tell you, one of the struggles we have in the ocean community is, I won't say it's easy to get funding to develop something, but a lot of times it's easier to get funding to develop something than it is to keep it in operation. And this is a big problem with these observing systems. But the kinds of nodes that are being envisioned are these nodes that include cabled observatories on the seafloor, profilers for the water column, suites of different kinds of sensors. Again, they're using different sorts of technologies, but there's problems. There's problems of data transfer, there's problems of power, there's problems of communication, so there's still a lot to be done. And again, one of the big projects is this project off of the Pacific Northwest to cable the tectonic plate and to really look at the sea floor. And a close-up look of that, which is from Neptune, courtesy of Neptune, I think there's a great image of what the future of the seafloor might look like at a hydrothermal vent. You know, how much can we learn about hydrothermal vents if we get to go out there, you get to go down in a sub, or you put a ROV down for maybe 4 days, maybe a week, if that's how long ship time you get. You leave. If you're lucky, you could come back within the same year. There's a lot to be learned by having instrumentation out there full time. And so here, you've got some chimneys, and you've got a cabled system, you've got a little robot, you've got some cameras. Imagine what this could tell us about the evolution and development of these hydrothermal vents. Their periodicity interruptions. How do the chemosynthetic communities develop? Is there succession over time? There are so many questions that could be answered with this sort of system. And I know that this kind of system creates so much data, is very intensive, and that's the kind of thing that Trident is really helping people manage. And not only manage the data, but make it interactive so that you can try and answer some questions through this sort of system. Well, a smaller system that I work with quite frequently is NOAA's Aquarius Reef Base off of Key Largo, Florida, and it's the only underwater research station in the world in operation. It sits about 4 miles offshore of Key Largo in about 60 feet of water. It's about 43 feet long, and teams of scientists go and live underwater for 1 to 2 weeks. And this gives them access to diving for 6 to 9 hours a day. So for instance, you could dive to 100 feet to do experiments for 6 hours, whereas from the surface, it's a lot less. Maybe you'd get an hour or 2 at the most. So the advantage of an undersea lab is it gives you time and access to, in fact, in this case, a coral reef, because around it is a coral reef. And there's a great project that's been going on for 2 years that's being done by Chris Martin and Niels Lindquist at UNC Chapel Hill on ocean acidification and sponge dynamics. And two interesting aspects of their work. They're using Aquarius not only to understand sponge dynamics, but as a test bed for technology. This is a prototype underwater mass spectrometer, one of only 2 in the world, and basically a chemical sniffer underwater. And one of the things they've been looking at is the dynamic of sponges on coral reefs. We think, in Florida Keys, that the population of sponges has risen over time. And so you think, oh, well, that's kind of interesting. Well, I'm not sure what difference it makes. Well, Chris and Niels have discovered that a large barrel sponge like this can pump through its system the equivalent of 1 Olympic-sized swimming pool in a day. Imagine the changes in the water chemistry that occur if you get an increase of sponges on the reef. And what they're finding is that the sponges may change the water chemistry such that it's not conducive to corals resettling. So there's some problems, though. This is really interesting work. The testbed technology is great. Well, let me show you a picture from their research that they were just doing last month. It's a rat's nest down there of cables. Everywhere you look, there's a cable. And as Chris told me, one fish decides to nibble on a cable, and you're done. We have a huge problem in shallow water oceanography, just in deep water. Not only do we need power, power is a big issue, but cables to calibrate the sensors, communicate between the sensors. We would love to do away with all of these cables. So power and cabling and data transfer are a huge issue underwater. Communication in general underwater is a problem. Just a little gee-whiz stuff about the undersea lab. Sitting over the lab is what we call the life support buoy, and it's connected by an umbilical to the habitat. And on there we have generators for power, compressors for air, and it's also our communication system. We transfer to a tower about 9 miles away on shore, and now we can transfer data. We can stream high-resolution video. And so because we're cabled, we're not wireless, we can stream data. In fact, Chris was telling me he was streaming data from the mass spec. Oh, I should go back and show you what the latest prototype was. I forgot to say that this is the next version mass spec right there. It's gotten even smaller. But he was streaming data to the manufacturer in Denmark live from underwater during his mission through this LSB system. Just so you know how it's kind of a cool thing how this works. The Aquarius lab, the inside air pressure is kept at the very same as the outside seawater pressure, so the water can't flow in. So to get in, you just climb in through the open moon pool because the water can't flow in. And so you can be standing right here, and there'll be fish swimming around at your feet. That is a really neat feeling. There's a nice workspace inside. There's a bunk room for 6 back here. It is a little tight. One of the other advances in technology that we have at Aquarius is out on the reef, can be 1,000 feet away from the habitat, are these undersea way stations. And 2 divers with all of their equipment can pop up in there to talk about what they're doing. Communication between instruments is a problem. Communication between divers is a problem. We're still searching for a cheap, easy-to-use, diver-to-diver communication system that is durable. We haven't found it. We can't find one we like. So you can go up in these things and communicate to your buddy. If you're doing a 6-hour dive, you can put snacks in there, water. But the best part about it is you have a special hose on your specially designed scuba tank that you hook up to a valve, and you turn a knob, and you fill your tank on your back and go back to work. There's none of this bringing the scuba tanks up to the surface and refilling, all done underwater. And for somebody who wants to work on a coral reef for extended periods of time, that's a huge advantage. So one of the big challenges in underwater research is this, the ability to communicate underwater and transfer data. So we would love to see, oh, I don't know what happened there. We would love to see better technology in this area. Current acoustic modems, I was talking to somebody about this, says low bandwidth, high power consumption, subject to severe environmentally induced outages. So we need better point-to-point, point-to-multipoint, be able to control submersibles, AUVs, positioning. One group right now is working on using green lasers and seeing if that might work. So this is sort of an area that there's a lot of interest in technology, and I will tell you, if it works, imagine if you had one of those little subs that could transfer high bandwidth data from wherever it was. You could drive around, send video, send sensor data in real time. It would be incredible. Lots of data to work with, but right now we're just not there. Another big area where there are challenges is information access. We need timely, topic-relevant, and data in the right format, not just for researchers, but for policymakers, managers, the public, industry, educators, in particular because the strategies we're moving towards in the ocean are adaptive, particularly where we want to integrate long-term monitoring data with ongoing research into our management problems. You know, how do you do that, getting the information access in the right format and the right time? To the managers from the researchers and back and forth, we don't have a system to do that yet. I know there's some people out in the audience who are working on some things like that. We need that to manage the oceans, particularly when we think about ecosystem scale modeling and management. You know, right now, that's one of those big words in Washington. Everybody, hot words is ecosystem-based management. We don't know how to do it. We know that we can't manage ocean ecosystems based on single species because when you impact one species, it cascades down the food web, and we need to manage in the overall ecosystem, but we don't know how to do it yet. And we don't know how to transfer the information to make that happen. A topic where we need this sort of interactive management style and information access is coral reefs and climate change. Coral reefs are facing a double whammy when it comes to climate change. High seawater temperatures causes bleaching. A healthy coral is this brown color because it has a symbiotic algae, zooxanthellae, within its tissues. When the corals get stressed, they basically spit out the zooxanthellae, and some can survive by feeding on zooplankton with their tentacles, their polyps, but many corals die from that. They also become more susceptible to bleaching and to disease. So that's one problem. So with climate change, you've got increased seawater temperatures can cause this coral bleaching, but we also now know that we're seeing a decrease in pH in the ocean. It's been measured to be about 0.1 pH unit, which means if you've got a decrease in pH, the water's getting more acidic. And if you combined increasing acidity with that temperature rise due to global climate change, the scenario for coral reefs is not good. If we go from 375 parts per million of CO2 in the atmosphere and about a 1 degree C change, we're okay. Things are still out there. You've got habitat and structure in the fish. Get up to between about 450 to 500 parts per million, 2 degree C change. Structure is starting to go away, and with that structure are all the organisms that it supports. And by the time you get up to about 500 parts per million, the reefs are gone, dead, kapooey. So it's not a good scenario. Again, it's that double whammy of temperature and acidity. But as we learn more, we need to be able to go back and change policies. And I'll give you an example is that it looks like some corals, when they bleach, they can bring zooxanthellae back on that might be more heat resistant than the ones that they originally had. So that means some corals might be more resistant to climate change. And if we discover that, those might be the corals we want to protect. So there needs to be a way to have interactive management and research. Well, here's an interesting information access problem for you. Okay, another one of my pretty cushy gigs. After having done some work in the Galapagos, I got hired by Celebrity Cruise Lines as their science advisor. Oh, I have to go to the Galapagos a couple times a year on their ship. It's terrible. But anybody here been to the Galapagos? Great, right? Well, as you probably noticed, when you go onto one of the islands, you have to have a Galapagos National Park Service guide with you. You're not allowed, unless you're doing research, and it's a great system. It protects the islands. They're very knowledgeable, so you have to go on with the guides. And on the ship, we have 5 or 6 guides on board, or 8, depending on what's going on. And they originally go through a course to get licensed, and then they get a little bit of a refresher each year, and maybe every 2 to 3 years, they get a workshop. They are starving for information about the Galapagos, scientific information. They're starving. I bring them my old science and nature journals. I send them articles. They have very spotty internet access. Sometimes it works, sometimes it doesn't. Sometimes it's fast, sometimes it doesn't. Me doing searches for Galapagos articles that have just come out and bringing them to them or sending them to them every once in a while is a really inefficient way of getting them material. You know, can there be a way to mine the information, mine the data, mine the literature that could be put in a pool on specific topics they're interested in? I don't know. But that's the kind of very specified information access that the needs are out there for, outside of the scientific community. It does bring up one problem, though, and that's the translation problem. I think we can do the data mining and the searching and all of that with a computer, but how do you translate the scientific articles into language that the guides might be able to read? And that, I think, we were talking earlier about having the human component. I think you're always going to have the human component to do that. But it's a huge need. I mean, I personally would love to see more people trained in that sort of translation field. Communicating to the public. Well, this really is my passion in how do we make science relevant and engaging? How do we find vehicles that work to get out to the public? To me, that's much harder than making it engaging and fun and relevant. Finding vehicles that work. Right now, if you look at the studies from NSF and other places, the general public gets, I'm sad to say, gets most of their scientific information still from where? Television. The surveys all show it's television. So we need to find ways to get to the public, not only through what they watch, but other ways to engage them. And certainly I think the internet and the web can be done to do that. And so that's, again, where I think all of you come in, new ways of using the web and using the internet to engage the public in some of this information. But we have to prove to them, and we have to inspire them, and I think have to inspire people like you that there's a reason we need to solve the problems in the ocean. We need to preserve and protect it for the future. And I could spout out, oh, it's the life support system of the planet, there's fish, and you've got to save the whales. You know what? That's not going to resonate with that many people. But let me show you some examples that I hope will. Fish and food are big business. 2 billion people rely on fish as the major source of their protein in the world. If there's more fisheries collapse, that's a major health crisis. 2 billion people, and certainly more than that, eat fish as part of a healthy diet. U.S. consumers spend $50 billion or more a year. Worldwide, fisheries and aquaculture support 520 million jobs. Seafood is number 2 behind oil on the U.S. trade deficit. This is big business. Okay, here's my proposal. Coral reefs need a bailout. They are worth $375 billion each year in economic revenue. We've been bailing out industries that don't meet that number anywhere near that. We need to bail out coral reefs. Fisheries, important protection from waves and storms, tourism and recreation, and millions of jobs. Whale watching. I've been doing research for a book. I never realized the numbers of whale watching. $2.1 billion worldwide industry. 13 million people participating on every year. Thousands of jobs across 119 countries, many of which are impoverished nations and communities that have very little other economic potential. This is huge business and very, very important economically across the world. Human health. Turns out that the ocean is the greatest potential storehouse of drugs on the planet. Horseshoe crabs. The copper-based blood from horseshoe crab is used to detect toxins in medicine. AZT, one of the important drugs in fighting HIV is based on research that was done on a Caribbean marine sponge. Other sponges have provided cancer-fighting drugs, anti-inflammatories. The lovely sea slug. It has a very large and simple nervous system, and the University of Miami ships out 25,000 sea slugs across the world for biomedical researchers doing studies on nerves and memory. And in fact, a scientist won the Nobel Prize in Medicine from, guess what? Doing research on a sea slug. And now my favorite, the cone snail, a vicious predator in the sea. Doesn't really look like it, but huge suite of venoms. The cone snail has this harpoon that it basically shoots out to catch and kill fish and other mollusks. But within that harpoon is a suite of venoms that has never before been seen in the animal kingdom. Not only do the different species have different venoms, in between their stings, the cone snail can actually change the chemistry of its venom. I don't know if anybody probably haven't heard of this. There's a new drug on the market called Prialt. It's one of the latest non-morphine painkillers. Guess where it comes from? The venom of the cone snail. Scientists think that this may be one organism on the planet that has the most application to pharmaceutical industry is the cone snail. Biomechanics, this one's fascinating. Turns out biomechanical engineers are looking at the flipper of the humpback whale to design better fan blades and the blades for large wind turbines. And another great one, biochemistry. There's no better name than the bone-eating zombie snotworm. Unbelievable. The first ones were found just in 2005, feeding on dead whale bones in the deep sea. Here you see these are all worms, tube worms, sticking up. They've got plumes at their top, and they've got very strange, fleshy bile green roots full of bacteria. The roots dig into the whalebone, and the bacteria digest oil and fat. Bone-eating zombie worms. They've just discovered some in shallow water that when are disturbed, they exude tons of mucus. Bone-eating zombie snotworms. Interesting application, though. The enzyme the bacteria use to digest the fat and oil is now being looked at to make a better detergent. Fascinating application of these organisms. On the zombie theme, the lovely hagfish, or some known as the slime hag. It's a jawless fish. It's a carrion eater. And so, but it can't bite through the skin of fish. So it has to find easier access. So it goes in through dead whale orifices, fish orifices, to eat the insides out. But by eating dead meat, it gets exposed to a lot of microbes. Turns out that the intestines produce broad-spectrum antibiotic compounds that are being looked at for the medical industry from the lovely hagfish. The other talent that the hagfish has is when it gets disturbed, it also secretes huge quantities of slime. Now, it has a really interesting way of dealing with that, because the truth is it can suffocate in its own slime. So it actually will tie its tail in a knot and then slip the knot up along its body to take the slime off so it doesn't suffocate. That's kind of cool. But what's interesting is the slime that it produces is actually these little packets of mucus combined with bundled up threads. And what happens is the seawater hits those packets, the threads untangle and spread apart, and it actually expands. So when you get this really disgusting slime, it's not all being produced by the hagfish. It's due to the absorption of seawater into the mucus and these threads. And so that material is actually being looked at as a potential replacement of a potential biodegradable replacement of polypropylene line. So really amazing applications of the biology of these organisms. Well, here is just a terrific image from Roger Hanlon at MBL. Roger studies the camouflage ability of squid and cuttlefish and octopus. And this would have happened in milliseconds. Here's an octopus that has just landed on a stone. Here's it's starting to camouflage itself, and here you can barely see it at all. And that would have happened in seconds. Here's another one. Here's another one you see up here. Here it is down there. You can barely see it camouflaged. Now, what's interesting, what Roger has discovered is it turns out that these organisms are colorblind. Optically, they visually can see the patterns on the bottom, and they match it visually. But if they're colorblind, how do they match the color? He doesn't know. He thinks that they might have color sensors in their skin that might be able to sense the color. The other thing that's interesting about these is that they only had red, green, and yellow pigments in their chromatophores. So how do they match the colors of the spectrum? Turns out they have reflectors in their skin. So it's a combination of pigments and reflectors. So you can imagine, let's say if they can color sense and you only need a couple pigments and match with reflectors, what would be the applications there? Oh, maybe PDAs, maybe nanotechnology. Imagine the car of the future that has a skin on it that could change color. Fascinating applications if it works. So I'd like to say there's an awful lot we can learn from the organisms of the sea, more than just harvesting them and exploiting their bodies, but for millions of years of evolution, what their biology can teach us for important applications in society and in technology. And some of the challenges we face, we've made a lot of progress in sensor development and integration, but there's still a lot of work to be done. The ocean observing systems, like Neptune, like some of the other coastal sites, are going to be producing huge data sets, and we need ways to integrate those not only for science, but into management and visualizations that we can use to educate the public. We really need work on this undersea communications issue and the transfer of data with high bandwidth. Long-term power supply. Again, we really want to get away from all those cables. At Aquarius, we've got that generator up on the life support buoy, and we would love to get away with that and just have a power source on the bottom. Information access and data mining. And again, this idea of how do we effectively reach the public with engaging and relevant information to get them engaged to help solve some of these problems. And I will reemphasize what was said earlier, and to inspire the next generation of scientists and the people that we want to go in on this industry. I just think this is so important. So with that, thank you. And if you're interested in the Undersea Lab, here's the website. It is uncw.edu/Aquarius. And if you like the whole story of the hagfish, the octopus, I have a new book that will be coming out called Slime, Sex, and Drugs in the Sea, and Why You Should Care. Be published by the University of Chicago Press, I hope, late 2010. Depends when I get my manuscript in. But the whole idea is to use these really fascinating marine organisms, connect them to uses in society, and then say, why is it so important that we protect them for the future? So thank you very much.
Okay, are there any questions for Ellen?
I know, it's almost drink time. Yep.
I once watched a presentation from people who work with extracting medicine from trees and how they go through zillions of experiments
Yep,
to find out one tree that's worth
that's right.
exploiting. And even then, you need to start killing all the trees in the world, I'm exaggerating, of course, in order to get usable enough.
Right.
So, do we have to kill all the snails in order?
No, I mean, and that's a great question, and that's a very important point that I'm sorry I didn't make. When we search for usable compounds from the sea, what we're searching for ones that can be synthesized in the lab. They don't do us any good if you have to harvest them from the sea. Yes, what the trick is, you go out and you collect as small amount as possible, then you study in the lab, and then the other part about it is you have to synthesize it. And even in the synthesis aspect, there could be problems. So that the industry or the community that is working on this, that's an integral part of it, is the ability to synthesize it in the lab once they've identified that compound. And I'll tell you, there are a lot of questions about this whole bioprospecting. Who has the rights to what's being found? You know, if it takes a submersible, you know, who has the rights what that submersible collect? I mean, there are a lot of questions about bioprospecting that still need to be answered.
Can I ask another question?
Sure.
The computer science side. If I were to choose, or if you were to choose, which is the most critical problem that you'd like to attack? So
Yep.
it would help solve all of your problems.
You know, this is a question I hate. I hate having to choose one over the other because these problems are interactive. And I'll give you an example, the whole issue of resilience of coral reefs. So let's say you fix the pollution problem, but if you have overfishing, it's not going to help you. And if your reef is stressed from other things, then hopefully we fix the climate change issue, but they're polluted, that's not going to help. So I'm going to defer to say I just can't choose one over the other. They're different scales, though. A lot of these problems are different scales. A lot of problems are local. You can fix overfishing locally, while the climate change thing is a global issue. And so one of the things, particularly in coral reef environment, is we're saying you have to do them both at the same time. You can't do one or the other, or it won't work. I can give you a couple. I would say climate change, overfishing, pollution, and habitat loss. Okay, and then there's invasive species. No, but those other four.
Tony, I mean, are there any solutions? I mean, you say you can control overfishing locally, but there's all sorts of major issues in monitoring and enforcing.
Right.
Can you use some of those deserts? Can you make those nutrient rich and encourage more fish in those huge areas of ocean that don't have anything?
Probably not. You know, experiments, you know, there's the whole iron seeding thing. And one of the issues, I mean, we don't know, it's a very interactive food web, and we don't know what the consequences are when you manipulate the environment. Another example is red tide. There's the issue, could you control red tide by things like ozone and clay? So let's say you smother the red tide in clay, what about everything else on the bottom? So the problem with, I mean, the scale of those areas is so big, it would be very difficult to do that. Plus, you know, I'm one of those people who says, I'm not sure I want to mess with Mother Nature in that sense. So I don't think that's the answer. I think the answer is cutting off subsidies for fishing, trying to, you know, check overcapacity, finding the fisheries that we can manage and commercially fish, and finding the ones that we just can't and what we can farm. I mean, I think we're going to have to solve some of these public domain and private rights issues about fishing. There's no easy answer, but I don't think manipulating the ocean in the other ways is going to work.
So I just had a question about, there seem to be sort of two ways of cognitive value of the ocean. One is sort of this, it's beautiful.
Right.
And the other is it has monetary value to bring it. And I'm wondering if you believe one of those.
You know, as somebody who works, I do a lot of work with the media, I do a lot of work with different groups in the public. I fully believe there are always going to be different messages for different groups. No one message is going to resonate with everybody. There are going to be some people who love the whales, and they want to do whatever it takes to save that humpback. That same person is going to be like, drugs from the sea, well, we can get drugs somewhere else. I think you have to cater your message for your different groups. And that's why, but I do think we haven't done a very good job about talking about things like preserving organisms, because the greatest cure for cancer may be in the ocean, swimming around somewhere, or stuck on the bottom somewhere that we just haven't found yet. And if we lose diversity in the sea, we're going to lose that potential cure for cancer. You know, we're going to lose those jobs associated with whale watching. I don't think we've made those arguments very well to the right people.
Thank Ellen just one more time.
Sure.
Thank you.